Hello everyone. In this chapter, we are going to talk about deformations, modification of rocks by folding and fracturing. Before we start to talk about deformations, I want to introduce you two principles of stratigraphy. They are the fundamentals to study deformations. First is the law of original horizontality. This principle says that the beds of sedimentary rocks deposited in water as horizontal layers due to gravitational settings. This means that the original sedimentary rocks layers are all horizontal. In reality, when the sedimentary rock layers are not horizontal, it must be a result of deformation. The second principle is the law of superposition. It says that in undisturbed strata, the oldest layer is at the bottom and the youngest layer lies at the top. If sedimentary rocks were depositing successively one layer on top of another from the bottom upward, the sedimentary rocks become younger and younger. Let's see this picture. It illustrates the sedimentary rocks record in Grand Canyon. The column with the numbers on the left to the rock illustration is the age of the rocks in millions of years. Before 500 million years, the sedimentary rock layers are all tilted. So based on the law of original horizontality, we know that after deposition of the rocks before 500 million years ago, there was an episode of a tectonic event that tilted the original sedimentary rocks. The erosion flattened the surface of the rock and followed by continuous deposition. After depositing all rocks records that the rocks are getting younger and younger towards the top. In the last, the river came in and carved the canyon in the sedimentary rocks and formed the Grand Canyon. This is how we use the principle of sedimentology and the cross-cutting relationships to understand the sequence of deposition and the tectonic events, as well as to get to know the history of the Earth. Now let's talk about the plate tectonic forces. There are three types of active plate boundaries, including convergent boundaries, divergent boundaries, and transform boundaries. Each type represents a type of relative motions between the plates. The relative motions are driven by different forces. In convergent plate boundary settings, the force is a compressive force. In divergent boundaries, it is a tensional force. And in transformed fault boundaries, the driving force is a shearing force. In the picture, we see that rock layers are twisted and folded. Based on the law of horizontality, we know that the rock's body must have been twisted and compressed, and the wavy layer of the rocks are called folds. Under the work of forces, rock body may break and dislocate. In this picture, the dark red-colored layer in the middle was originally continuous and horizontal, and we can see there are three displacements of the rock layers now. It looks like the rock blocks on the right has slided down along the broken surfaces. And in geology, the broken surface of the rock and where the relative movement occurred, we call it a fault. To study the deformations of the rock, we need to quantify the deformation and locate where the deformation occurred. For example, in this picture, the two little kids are standing on a tilted limestone bed. In between the limestone beds, there are interbedded shale. These sedimentary rocks, layers of limestone and shale, were originally horizontal. To quantify the deformation and the displacements of its original place, we can measure the strike and dip of the rock layers. Strike is the compass direction of rock layer as it intersects with an imaginary horizontal surface. Dip. Dip is the amount of tilting of the layer and is measured at a right angle to the strike. So when the strike and dip of a tilted layer, a fault plane, or other surfaces were measured, based on the measurement, the measured surface can be drawn in 3 dimensions. For example, the tilted limestone in the picture is measured, and the result shows that the strike direction of the tilted layer is 90 degrees from north, which is towards the east, and the dip direction is to the right of the strike, and the dip angle is 45 degrees. Knowing the strike and dip measurements, the surface of the tilted limestone can be replicated and drawn in 3-dimensional system. Therefore, in a geologic map, we only need to draw a straight line along the compass direction of the strike. Then draw a short tip mark in the middle of the straight line to represent the dip direction, and write down the dip angle next to the dip direction mark so that the 3-dimensional tilted layers of the rock can be represented in a flat map. Now let's see how do rocks get deformed. The rock mechanical behavior can be different under different conditions. First off, in this picture, the undeformed rock is on the right. The second to the right shows the ductile behavior of the rock under a compressive force from the bottom and the top. The rock is not broken, but the middle part of the rock is bulged and by short. This is more likely to happen in the deeper part of the crust, where in addition to compressive forces, the surrounding confining pressure is high. To the very left, the rock sample is fractured and it showed brittle behavior under the compressive force. This is more likely happened near the surface of the crust, where the confining pressure is low. Therefore, surrounding confining pressures can change the behavior of the rocks. Experiments also suggest that the temperature promotes the ductile behavior of the rock, while the rock tend to be more easily being broken under tensional forces. Now let's talk about the basic deformation structures. Fold and faults are basic deformation structures that geologists map to understand crustal deformations. A fault is a surface across which rock formations have been displaced. The surface is also the fault plane. There are different types of fault, classified based on the dipping angle of the fault plane and the slip direction. When the dipping angle of a fault plane is less than 90 degrees, the rock formation blocks on top of the fault plane is the hanging wall, and the rock formation block underneath the fault plane is the footwall. If a hanging wall slided downward on the fault plane relative to the footwall due to tensional force, it is a normal fault. If a hanging wall moved upward against the fault plane relative to the footwall due to compressive force, it is a reverse fault. When the steeping angle of the fault is smaller than 45 degrees in a reverse fault, it is a thrust fault. When the dipping angle of a fault plane is nearly 90 degrees and the two blocks slips horizontally, the fault is called the strike-slip fault. If the two blocks slip motion is to each other's left, it is called the left lateral strike-slip fault. If the two blocks slip motion is to each other's right, it is called the right lateral strike-slip fault. Oblique slip fault is when the two blocks of the fault experience the combination of deep slip fault movement and strike-slip fault movement. The two faulting blocks moved horizontally and perpendicularly relative to each other. In the picture, this fault experienced a combination of normal faulting and left lateral slip motion due to the tensional and shearing forces. Folding is a common deformation structure observed in nature. By the law of original horizontality, we know that all the layer sedimentary rocks were horizontal when they were originally deposited. The tectonic forces result the horizontal layer structures into curved layer structures, which are called folds. The two sides of the folds are limbs, an imaginary surface that divides the fold as symmetrical as possible, with one limb on either side of the plane is the axial plane of the fold. The fold axis is the line that the beds intersect with the axial plane. Rocks that upfold into arches are called anticlines. Those that downfold into troughs are called synclines. A symmetrical horizontal fold has a horizontal fold axis and a vertical axial plane with limbs dipping symmetrically away from the axis. If the axis is not horizontal, it is called a plunging fold. With increasing amount of deformation, the folds can be pushed into asymmetrical shapes, with one limb dipping more steeply than the other. This can also occur if the direction of the deformation forces is oblique to the layering of the beds. Such asymmetrical folds are common. When the deformation is intense and one limb has been tilted beyond the vertical, the fold is called overturned fold. Both limbs of an overturned fold dipping in the same direction, but the order of the layer in the bottom limb is precisely the reverse of the other original sequence. In this case, we will see older rocks are on top of younger rocks. Within a dome or anticline structure, when erosional process remove the top of the structure, older rocks will be exposed to the surface. When this happens, the center of the dome and the axis position of an anticline will have older rocks exposed than the rocks away from the center and axis. In the picture shows a dome structure. Formation number 1 is the oldest, and it is exposed in the center. From the center outwards, formations number 2, 3, 4, 5, 6, 8 are gradually getting younger and younger. This is because that erosion removed the top young layers of rocks from the dome and the exposed older core. In this picture, it shows a basin. Within the basin, the youngest rock is exposed in the center of the basin, and from the center of the basin outward, the age of the exposed rocks are becoming older and older. This is because that the center of the basin is filled up the last. Similarly, a syncline will expose the youngest rock at the axial position, and the age of the exposed rocks are older and older toward the limbs. It is due to the erosion to the limbs of the syncline. In continental scale, extensional forces lead to series of normal faults, which is also called horse and graben. Compressive forces will lead to thrusting and reverse fault. Sometimes, compression leads to elevation increase, and the gravitational potential induces the collapse, and therefore we can also see normal faults developed due to the gravitational force in a compressive tectonic setting. Transform fault is dominated by lateral movement of the faulting blocks. However, because transform faults often have stepovers, such as the area that is marked with red and blue arrows in the picture, the red arrows along the major transform fault, the San Andreas fault, marked where experienced localized extension due to lateral movement of the fault blocks, while the blue arrows marked where experienced localized compression due to the lateral movement of the fault. So within a strike-slip fault system, there will also be localized extension and compression. Okay, in this lecture, we learned the different types of the deformation structures and their causes and formation characteristics. I hope you enjoyed this lecture and see you next time.